6,000 people. One ship. 7 days from the nearest port. Not a single drop of drinking water on board came from a tank filled at shore. Every shower running right now. Every tap. Every glass of water poured at dinner. Every ice cube dropped into a cocktail at the pool bar. All of it was the Atlantic Ocean less than 24 hours ago. Most people never think to ask. The tap works. The water is cold. The shower is hot. The experience feels exactly like a mid-range hotel on dry land, and that is entirely by design. But the moment you start pulling on that thread, you find something hiding underneath this ship that changes how you see the entire thing. A cruise ship is not a floating hotel. It is an industrial water factory that also sells vacations. And understanding how it solves that problem reveals one of the most quietly staggering pieces of engineering hiding in plain sight on the modern ocean. Start with the number that breaks everything. A large Royal Caribbean or Carnival cruise ship carries around 6,000 passengers. Each one uses between 50 and 66 gallons of fresh water every single day. Showers, taps, toilets, laundry, drinking. Run that math at full scale. 6,000 people, 66 gallons each, every single day. That is just under 400,000 gallons daily. Before the crew is counted, before the kitchen's producing 3 meals a day for every person on board, before the pools, the spas, the industrial laundry running around the clock, the engine cooling loops, the fire suppression systems. The real daily water demand on a ship like this rivals the output of a small municipal water treatment plant, serving an entire American town. Except the municipal plant does not move. It does not pitch and roll in a mid-Atlantic swell. And it is not surrounded on all sides by the one substance it absolutely cannot use. So the obvious assumption collapses. Surely the ship is just carrying all this water, loaded at port, stored in enormous tanks below the waterline. It cannot. The numbers make it impossible. The largest cruise ships store around 132,000 gallons of fresh water in hull tanks. That sounds serious until you do the division. It covers less than one full day of demand. Even if you tried to load enough water for a full 7-day voyage, the weight alone becomes catastrophic. Fresh water weighs approximately 8 1/3 pounds per gallon. Multiply that across 7 days of full passenger demand, and you are adding millions of pounds of cargo to a ship that has already calculated its weight distribution down to the last ton. The fuel gets displaced. The cold storage disappears. The structural balance collapses. You would not have a cruise ship. You would have a barge full of water that could barely move. The ship cannot carry its supply, so it manufactures it continuously, every single hour of every day at sea. Here is the first wall the engineering has to climb. The ocean surrounding the ship is not simply water with a little salt mixed in. It is physiologically dangerous. Drinking seawater does not hydrate you. The salt concentration forces your kidneys to expel more water than the drink ever put in. Seawater actively accelerates dehydration. Drink enough of it, and your organs begin to fail. You are floating on the largest water source on the planet, and every drop surrounding the hull will make you sicker the more of it you consume. That is the starting condition. A ship surrounded by an endless supply of the wrong kind of water. Now build an industrial production system on top of it. Keep it running in rough seas, and make it completely invisible to 6,000 people trying to enjoy their vacation. The older and still widely used solution is flash evaporation. What makes it elegant is that it runs on energy the ship was already throwing away. The massive diesel engines driving a vessel like the Symphony of the Seas generate enormous heat simply by running. That heat has to go somewhere, or the engines destroy themselves. A jacket cooling water system circulates constantly around the engine blocks, absorbing thermal energy and carrying it away. That cooling water runs at between 167 and 203 degrees Fahrenheit, not quite boiling under normal atmospheric pressure. but close enough to matter enormously once you understand what the engineers did with it. Ship engineers looked at that waste heat and realized it did not have to be dumped into the sea. It could be redirected into something the ship desperately needed. Inside a flash evaporator, seawater is fed into a sealed chamber held under vacuum. Under normal atmospheric pressure, water boils at 212 degrees Fahrenheit. But under vacuum, the boiling point drops significantly. The incoming seawater, already warmed by the engine cooling loop, enters that low-pressure environment and does not slowly climb toward a boil. It flashes instantly. In a fraction of a second, it converts to steam. The salt cannot flash. It stays behind as concentrated brine. The steam rises, hits a cooler condenser surface, and converts back into liquid water. Pure. Distilled. Stripped of everything the ocean had dissolved into it. That water is collected and pumped toward the storage tanks. The brine moves to a second chamber at even lower pressure and flashes again. A third stage extracts whatever heat remains. Maximum output from energy that would otherwise vanish into the sea. A large cruise ship runs two of these systems, one forward, one aft. If fire or flooding compromises one engine compartment, the other keeps producing. Losing water production at sea is not a logistical inconvenience. It is an emergency that threatens the entire voyage. That redundancy is survival engineering built into the bones of the ship. Each evaporator produces between 5,000 and 6,600 gallons of fresh water per hour. Colder seawater in northern latitudes absorbs more heat from the engine cooling loop, meaning a North Atlantic crossing can outperform a Caribbean route in raw water output. The temperature of the ocean becomes a variable in the production equation. The second method works through pressure instead of heat. In a reverse osmosis plant, raw seawater is pumped to extreme pressure and forced through a semi-permeable membrane, a material engineered with pores small enough to allow individual water molecules through, while physically blocking salt ions, bacteria, viruses, and dissolved solids. The rejected brine is discharged back into the ocean. The water that made it through is collected on the other side. Reverse osmosis systems are more compact than flash evaporators and do not depend on engine heat, giving them flexibility the evaporators cannot match. They demand serious continuous power to maintain membrane pressure, but that trade-off is worth the redundancy they add. Most large ships run both systems in parallel. The evaporators carry the primary load. The reverse osmosis plants handle backup and peak demand. Combined, major lines like Royal Caribbean produce up to 90% of all onboard water this way, independent of any port or shore infrastructure. Both systems feed water through a continuous salinometer, monitoring salt content in real time. The acceptable threshold is 10 parts per million. If salinity climbs above that, a three-way valve fires automatically and redirects the flow overboard. The batch is dumped. The system recalibrates and keeps running. Nobody in cabin 714 notices. The machine corrects itself silently below decks. Now here is the part that stops most people cold. After all of that engineering, after the vacuum chambers and the pressure membranes and the continuous monitoring, the water coming out is not ready to drink. Not because something went wrong, because it is too clean. Completely distilled water, stripped of every dissolved mineral, is corrosive to metal pipe infrastructure. Run it through miles of copper and steel, and it slowly dissolves those pipes from the inside, pulling minerals out of the metal to replace what is missing. It also tastes completely wrong. Flat, slightly metallic, empty in a way that is hard to describe before you experience it. And in large quantities, fully demineralized water does not behave the way the human body expects. The ship spent enormous energy removing everything from the ocean to produce pure water. Now it has to deliberately put a controlled set of things back in. The water passes through mineralizer beds, containers packed with calcite granules that dissolve measured amounts of calcium and other minerals back into the water as it flows through, rebuilding the mineral profile that makes water taste correct and behave safely inside a plumbing system. Maritime engineers call this rehardening. Carbon dioxide is injected to bring the pH into the safe range between 7.2 and 7.6. Then chlorination, maintaining a free chlorine concentration of around 2 to 2.5 parts per million, sometimes reinforced with ultraviolet irradiation for additional disinfection. Disinfected, mineralized, pH balanced. What was open Atlantic Ocean 48 hours ago is now moving through miles of pipe towards 6,000 cabins, 100 restaurant stations, dozens of bars, and every tap on every deck. That faint difference you may have noticed between water from a ship tap and water from your faucet at home. Slightly mineral forward, a trace of chlorine. Something you might not consciously register but somehow sense is slightly off. That is not a flaw. That is the system's fingerprint, the chemical record of every step it took to get there. One more detail we're sitting with. Modern cruise ships fill their swimming pools with fresh water. A vessel surrounded by unlimited ocean, running industrial desalination around the clock, deliberately uses that manufactured product to fill the pools on the upper decks. Not for passenger comfort, for corrosion control. Saltwater destroys pump impellers, filter housings, and pipe fittings at a dramatically faster rate than fresh water. The maintenance costs and shortened equipment lifespan make using ocean water in the pools more expensive over time than producing fresh water to fill them. Desalination as a maintenance strategy, not just a hydration one. And there is the geography the system fights constantly. Flash evaporators cannot operate within 4 nautical miles of shore because nearshore water carries sediment and contamination that fouls the chambers. Reverse osmosis plants require a minimum depth of around 164 feet before intake water is clean enough to protect the membranes. Every port visit shuts primary production down. The clock starts. Production resumes only once the ship clears the threshold and deep open ocean lies beneath the hull. The ship is not just building water. It is building water against a deadline, against geography, against the physics of salt and pressure, and against the reality that 6,000 people have no idea any of this is happening 100 feet below where they are standing. You turn the tap. Water comes out. Cold, clean, faintly different from home in a way you may never have registered before now. That difference is real. It is the trace of a machine working invisibly beneath decks you will never visit, solving a problem you were never supposed to think about. Every single hour of every day at sea. Now here's what nobody mentions. That water has to go somewhere after 6,000 people finish with it. One 7-day voyage generates over 210,000 gallons of waste from toilets alone. Over 1 million gallons of gray water from showers, sinks, and laundry. The factory runs in both directions simultaneously. And how a sealed floating city processes all of that in open ocean without contaminating everything beneath it is a system just as engineered, just as invisible, and just as remarkable as everything that made the water. If the hidden machinery behind everyday things is what brought you here,